We've dealt with the circle, we've dealt with the ellipse. Now we're moving on to our next conic section, that of the parabola. And to just kind of keep in mind the tracking of the generation of these different sections, let's just kind of start here with our conic surface. I'm going to make a whole bunch of cuts or sections through point P over here. So if we cut parallel to the base, we get this red circle, and you can see there's exactly one focal point for a circle, the center. And then this purple section is cut at an angle, such that it cuts both sides of the axial triangle, and that generates an ellipse, as we know. And you can see the two focal points there. But what if we continue to tilt that cutting plane steeper and steeper and steeper? Right? If we cut it a little bit steeper, we're going to get a longer ellipse, conic or focal points right around there. Let's bend it even more. Focal point's going to be more like here. And we can keep going. I'm not even going to bother anymore. All right, you can see that as our ellipse gets stretchier and stretchier, the focal points get further and further away from each other and kind of closer to those vertices. So we have all these stretchier and stretchier ellipses. But what if this cutting plane were cut so that it's going to be parallel to this side of the axial triangle? That is, it's not going to cut it. Well, if it's not going to cut it, then it's not going to generate an ellipse. So essentially, I'm just going to bring P prime down here. So we're going to make our diameter parallel to that side of the axial triangle, which means we're going to get this curve. Right? That's a straight line by there. So what just happened? What happened to this other focus point? It's getting further and further away from the center, further and further away from the other focal point, obviously. But if we bend it into the point where this cut is now going to be parallel to that other side, so this bows out just a little bit too much, it's bothering me. There we go. That looks a little bit better. I'm just going to erase that. Once we make this cut parallel to that side of the axial triangle, what happens to this other focus point? It doesn't just disappear, but it doesn't really exist around here anymore. As long as this conic surface continues, this curve, this parabola, is going to continue. So it makes sense that this focal point is still going to be around here, but where's the other one? It is infinitely far away. Might sound counterintuitive, but it is still in existence. It's just infinitely far away from this one because of the nature of parallel lines and therefore parallel planes. All right, and we're going to revisit that and think about how does that affect the focal property. But at the very least, we still have this one. So whatever we say to define this curve, it's going to use this point. But it's not going to be quite the same as for the ellipse. Because remember, for the ellipse, that is running out. The focal property was that the sum distances from any point on the ellipse to the two focal points is constant. Right? So D1 and D2, and that's always going to equal the major axis, right? That sum is going to be constant. But in the case of the parabola, d2 is always going to be infinitely long. If we pick some point on the parabola and we draw a point, a line from that point to this focal point, call this d1, d2 is going to be infinitely long. So this way of using the focal points isn't really helpful because every sum is going to be equal in that they're all going to be infinite, but it doesn't really help us describe what this curve looks like. But we are going to use this focal point, and it is going to be a little bit different. One piece of good news is that when we want to graph a parabola, we are already acquainted with the equation. You may have guessed it. It is none other than the quadratic. This gets us a parabola. Before I was calling it U-curve or the quadratic curve, but now we know that, well, we haven't proved it yet, but we do know that the quadratic curve, the U-curve, is the exact same as a parabolic curve. We're going to get into using this to help us define what this curve looks like. We have a function, we have a focal point, but now we need to make up or come up with some kind of rule to define the shape of this curve. To understand the focal property of a parabola and how that point helps us define the shape of a parabola, I'm going to start us off with one that is very carefully chosen by myself. Y is equal to 1/4 x squared. I did a little t-chart and generated several points. Check my math if you don't trust me, but it should all check out. And I'm going to tell you right off the bat where the focus point is. It's going to be right here at 0, 1. And you can see the purple parabola is sketched here. I labeled a few points from our t-chart. And this is how the focus point helps describe this curve. Basically, any point on the parabola is going to be equidistant to the focus and to some straight line outside of the parabola. Now that all might sound kind of jumbled, but here's essentially what it means. Pick point A. If we were to draw a line from F to A, that distance is going to be the same distance from point A to some straight line outside of the parabola. Now, everything up here is going to be within the conic surface, so we have to go outside of the curve, and it's going to be down here. Now, the shortest point, or shortest line between any two, the shortest distance between any 2 points is the straight line between them. Sorry, that was really awful. Let's touch this up just a little bit. So we're going to draw this other line straight down, but hopefully let's make it actually straight. All right. Just for our purposes, I'm just going to call this point M down here. Now, my claim is that FA is going to be equal to MA. All right? And we're going to check that in a second. But if that is true, then BF is going to be equidistant to BN. Let's call this N down here. And likewise, CF is going to be equidistant or equal in length with CP. All right. Let's put P down here. All right. So my claim is that this red dotted line down here is that straight line outside of the parabola where that consists of a set of points that are equidistant from every point on the parabola to the focus point, which means that FA is equal to AM, FB is going to be equal to BN, and FC is going to be equal to CP. All right, so that is quite a claim. Let's see if it's true. We know the distance formula, so we're going to do the distance formula 6 times. So you can pause the video now and check it out, or do at least one of them, just to make sure the math checks out. But I'll put up a couple over on the side to make sure that these distances are in fact equal. So let's give that a shot. So, doing a couple of these, calculating these distances, we can see that this checks out. Every point on the parabola, the distance between it and the focus point is going to be the same distance from it to this red dotted line. And to start off with the most obvious one, if we just take the point here at the vertex, FV is clearly equal to 1, and DV is also equal to 1. So that's kind of like the very first one. That's pretty obvious. FA, you can see the distance formula done out here. It ends up equaling 5/4 over here. And then MA, since it's a vertical line, it's pretty easy to calculate it. This is going to be 1, and this is 1/4. So it also is 5/4. FB, I picked these ones to make them easy for us. It's going to be 2 units, 2 units. So that checks out. And then FC, if you do the distance formula, you get 13/4. And then PC also ends up being 13/4. All right, so this does check out. No other point is going to have this characteristic as the focus point. And this red dotted line that we have down here is called the directrix. All right. But now the question is, how can we find out what this focal distance is? For the ellipse, we discovered that it's going to be the focal distance squared, or rather the distance from the center to the focus squared is going to be the difference of b squared minus a squared. But here, our b is infinitely far away. We really only have, well, and so is the center of this section, if we can talk about this parabola having a center. So we're going to have to use something different. Now, I did deliberately choose this one so that the numbers work out nicely, so that this focal distance is exactly 1. So let's look into how we can find or derive that focal distance when we're confronted with an equation that would get us a parabola. Coming back to our original equation, y is equal to 1/4 x squared, something about this determined this focal distance. And the only thing that's really an aberration is this 1/4. So something about that 1/4 made the focal distance 1. But in the interest of time, I'm just going to kind of tell you the relationship between this number and the focal distance so that we can kind of move along a little bit faster. So let's kind of look at a universal quadratic or equation for a parabola. Whenever numbers be multiplied by x squared, let's just call that a. And I'm going to just make up a term, p. I'm going to say that p is the distance from the vertex to the focus. So this distance here is our p. And therefore, it's also going to be the distance from the vertex to the directrix, right? Excuse me. So, here's the relationship. P is equal to 1/4 times the reciprocal of A. Now remember what a reciprocal is. Mechanically, you're just turning the number upside down. But what it really is, it's a number that when multiplied by the original gets us a product of 1. So A times 1 over A will get us A over A, or 1. But this is the key thing that we want to remember. P is equal to 1/4 times the reciprocal of A. All right. And again, we don't have enough time to kind of get into where this comes from, but we'll kind of take a look at a clue in a minute. But let's apply this to our equation up here and see if this holds true. So we're looking for P, which we know is going to be 1, right? The distance from 0 to 1 is 1. We know this is going to equal 1, but let's just give this a shot. So 1/4 times the reciprocal of A. In this case, A is 1/4. So we can say 1/1/4, but really that's the same thing as, just take the reciprocal of A, which is going to be 4/1. And we can see that this is going to get us 4/4, which is equal to 1, which is what we knew this was going to be. So at least in this case, this does hold true. But basically, when you come across an equation for a parabola and you want to know what the focal distance is going to be, this is going to be your key. So just as an example, I haven't prepared an example in advance. I'm just going to make up some numbers. How about 3x squared? All right. So we know how to do this. P is going to be equal to 1/4 times the reciprocal of A. In this case, the reciprocal of A is going to be 1/3, so 1/12. This means that if we were to graph this quadratic, right, and obviously this is going to have a vertex of 0, 0, much like the one that we started with. Like I said before, we're going to do this with all of our conic sections as we're graphing them. If we were to graph this, pretend that's there, the focal point is going to be up here at 0, 1/12, right? We know that for sure, which means that down here at 0, -1/12 is going to be the point through which the directrix is drawn. Or in other words, if we were to write the equation for the line that is the directrix, it would just be y is equal to -1/12, right? This line is that horizontal line going through -1/12 on the y-axis. And so we can graph our focus point and our directrix, and it's going to have this same property. The distance from here to here and here to here are going to be equal lengths. It doesn't look like it ought to be true. In fact, it looks a bit counterintuitive, but this is one of the surprising turns that often happens in mathematics, where something kind of unexpected happens. When you first saw this, and again, this probably has more to do with my drawing abilities and things not actually being equal intervals, but this line does not, I wouldn't have guessed necessarily that it's going to be equal to this one, or certainly not those two, but they are. There's still a lot of symmetry, a lot of equality going on here. This focal property helps us define what the parabola looks like. And it all depends on this one focus point and this one line called the directrix. Now, hopefully you're teaming with at least a few questions. The first one that comes to mind is, well, what the heck happened to the other focus point? And is it still playing a role for our parabola? And the answer is yes, and we're going to look at that in just a second. The other question is, what's up with this directrix? Where did it come from? And why don't the other conic sections that we've looked at have one? Well, technically, they kind of do, except that in those other cases, if we were to have something like the directrix that kind of plays the same role, it's not going to be a straight line. And maybe you can see that pretty quickly if we were to think about a circle, right? I'm just going to erase the stuff over here. just turn this over a little bit. All right. So if we have, here's the center, here's a circle. If we wanted to describe something like the directrix, that is a line that is equidistant to every point on the circumference as every point on that circumference is to the focus point, that is the center of the circle, well, we can see pretty quickly that's just going to be another circle that has twice the radius. So if this is r, just take another r and describe that circle. This we could call our directrix circle, right? And that makes sense because any point on the circumference of the black circle is going to be equidistant to the center as to some point on the directrix circle, right? These lines are always going to be equal. So that makes sense. What would that look like for the ellipse? Would there be a directrix circle or a directrix ellipse? What's going on? But then somehow, by some kind of magic, this curved figure that has the same property of the directrix turns into a straight line when we get to the parabola. That's kind of weird. But also, maybe it's not too surprising because once we get to the parabola, we're dealing with an infinite curve. Once we get into the realm of the infinite, things get weird. Straight lines become curved lines become straight. We're going to take a look at that in just a second. All right, so maybe you can think about that on your own, but now I want to just take another look at the significance of this focal property and what happened to that other focal point. So let's take a look at that.